You have never experienced the universe in real time. Every face you see is a tiny bit in the past, and every star is an ancient postcard. That delay is not a glitch in your senses. It is enforced by one number that rules everything. Break that number, and you could break cause and effect. You could receive a reply before you sent the message. You could turn physics into a paradox generator. Tonight we chase the speed of light, and we find out why it quietly rewrites time and space. If you like deep stories that make the universe feel weird again, please like this video and subscribe. Most of us meet the speed of light as a fact to memorize, then we move on. Maybe you remember a number like 186,000 miles per second from school, and it feels like a fun flex at a party that would not invite you a second time. Scientists toss this number around when talking about the universe, and it can start to feel like a piece of trivia that belongs on a poster next to a glowing nebula. But the speed of light is not a trivia fact. It is not even primarily about light. It is about information. It is the maximum speed at which any influence can move through space. It is the fastest possible delivery service for cause and effect, which means it is the fastest speed at which reality can update itself. That sounds abstract until you notice how much of your life depends on signals arriving. Your eyes do not touch the world. They collect light that left surfaces earlier. Your ears do not touch the world either. They collect pressure waves that take time to cross the air. The difference is that sound is slow enough for your brain to feel it. You see lightning, then you wait for thunder, and your mind can almost measure the distance just by counting. Light is so fast that your instincts treat it like magic. Flip a switch, and the room blooms instantly. Look at a screen and it feels immediate. Even when something is far away, light still arrives quickly enough to fool you into thinking there is no delay at all. Based on everyday life, it makes perfect sense that earlier humans believed light simply appeared. Now here is the first crack in that comforting intuition. Light is not infinite. It moves at a finite speed, and that speed is fixed. In a vacuum, the speed of a light is exactly 299,792,458 meters per second. Not about, not roughly, exactly. The number is so fundamental that modern physics treats it less like a measurement and more like a rule. Once you accept that, the world starts to feel different in a quiet, unsettling way. If there is a maximum speed, then there is a maximum speed for every message, every warning, every goodbye, every bit of news from the cosmos. The universe is not a single stage where everything happens at once. It is a giant system where information moves, and the movement takes time. Even inside our own neighborhood, you can feel the limit. When a spacecraft on Mars sends a message, it cannot arrive instantly. Even in the best case, a round-trip exchange takes minutes, and depending on where the planets are in their orbits, the fastest possible reply can take tens of minutes. You ask, you wait, you receive, you respond. No antenna can fix that. No clever coding can fix that. It is not a technology problem. It is geometry plus a speed limit. And the speed limit is not only annoying, it is protective. Because if you could send information faster than light, you could build situations where the order of events becomes unstable. Two observers moving relative to each other do not agree on how time is sliced up across space. Mix that with faster than light signaling, and some observers will see the reply arrive before the message is sent. That is not a cute loophole. That is a contradiction. So the speed of light is doing two jobs at once. It is a speed, yes, but it is also a guardrail. It keeps the universe from collapsing into paradoxes where effects outrun causes. In a very real sense, it is the speed of causality. Now zoom out and let the loneliness hit. The nearest stars are so far away that even light needs years to cross the gap. That is why science fiction invents shortcuts like hyperspace and warp travel, because otherwise every interstellar story becomes a story about waiting. But real physics does not negotiate. Real physics says this constant is baked into reality itself. And here is where it gets properly strange. The moment you accept that the speed of light is the same for everyone, no matter how fast they are moving, you are forced into a trade. If the universe will not let the speed of light change, then something else has to. That something else is time and space and the idea of a single universal now. This is the part where our instincts usually protest. A speed limit should not rewrite the nature of time, right? It should just slow down travel and communication. But the universe is not only limiting how quickly light moves, it is limiting how quickly any information can move. That single rule has consequences that spread outward like ripples, and those ripples reach everything we thought we understood about motion, distance, and the order of events. By the end of this journey, you will understand why ordinary phrases like "at the same time" or "right now" are more fragile than they sound. You will understand why you cannot keep adding speeds together and ever reach light speed. You will understand why the dream of visiting even nearby stars in a single human lifetime crashes into physics. Not because we are weak, but because the universe is built this way. But we are not starting with Einstein. We are starting with a much simpler human belief, the one that feels obvious in your bones. Light arrives instantly. It just appears. In the next part, we're going to watch that belief stand strong for centuries and then begin to crack, not because people got less stubborn, but because they got more clever. For most of human history, the speed of a light was not a mystery. It was a non-question. You lit a torch, and the glow was there. You looked at the sun, and the world was already bright. Nothing in daily life gave your senses a reason to suspect delay. So the simplest story won for a very long time. Light must be instantaneous, or at least so fast that it might as well be. And once an idea like that becomes the background assumption of a culture, it turns invisible. People stop testing it. They stop doubting it. It becomes one of those quiet beliefs we build everything else on, like the idea that time ticks the same for everyone. But even in the ancient world, there were hints of rebellion. A few thinkers considered the possibility that light had to travel, which would mean it needed time. That suggestion sounds obvious to us now, but back then it was almost offensive because it implied the universe had delays built into it, and delays felt like imperfections. Then came the weight of authority. Aristotle argued that light propagation was instantaneous, and when a voice like that echoes through centuries, it can harden into a kind of intellectual gravity. Not because everyone is lazy, but because knowledge is social. If the brightest minds agree on something, most people will build on it instead of tearing it apart. Still, the idea never fully died. You can feel it in the way later thinkers kept circling back to the question. They noticed something important. Light behaves differently in different materials. It bends, it slows down inside glass, it changes direction in water. Those observations did not prove anything about speed in empty space, but they whispered a dangerous possibility. If light can behave differently depending on what it passes through, maybe it is not some instant divine flash. Maybe it is a traveler. The problem was not imagination. The problem was tools. Because how do you measure something that moves so fast your body cannot detect it? If you want to measure the speed of sound, you can clap and wait for the echo. If you want to measure the speed of a galloping horse, you can watch it cross a field. But light crosses a field in a blink so small it does not even feel like a blink. This is why one of the first serious attempts to measure light speed feels both brilliant and almost adorable. Galileo described an experiment that sounds comically simple because it uses the most basic equipment humans have always trusted. 2 people, 2 lamps, 2 hilltops. The idea was straightforward. 2 observers would stand on distant hilltops near Florence, each holding a lantern that could be covered and uncovered quickly. One person would uncover their lantern. The other person would watch for the flash. The moment they saw it, they would uncover their own lantern in reply. The first person would then look for that return flash, and time the whole sequence. If you know the distance between the hilltops, and you can measure the delay, you can calculate how long light took to travel the round trip. If light were instant, there would be no delay beyond human reflexes. If light took time, even a tiny time, the delay would grow as the distance grew. Galileo was not chasing perfection. He was chasing the first crack. Any measurable lag would have been revolutionary, so he tried it. And this is where the universe shows you what it thinks of your cleverness. At distances of less than a mile, light would make the trip in about 5 microseconds. That is 5 millionths of a second. Your brain does not perceive that. Your muscles do not respond that fast. Even if you are fully focused, even if you're trying your hardest, you cannot move your hand in 5 microseconds. You cannot even begin to begin. Human reaction time is closer to 200,000 microseconds, which is about 0.2 of a second. In other words, Galileo was trying to measure a delay that was roughly 40,000 times smaller than the delay created by the nervous system of the people doing the measuring. So what happened was inevitable. The experiment returned a result, but the result mostly measured humanity, not light. The tool simply was not sensitive enough. The best he could say was that if light had a finite speed, it was extremely fast. And that might sound like a failure, but it was a very specific kind of failure. It was the failure of a good question asked too early. Galileo had aimed his mind in the correct direction. He just did not have the instrumentation to catch the answer. Later, the experiment was repeated by other scientists with similar methods, hoping they could push the distances farther and reduce human error, but the same wall kept appearing. You could extend the distance, yes, but you could not extend it enough. Not without leaving Earth itself behind. This is the moment where the story turns from a quaint human struggle into something epic. Because if Earth is too small for this measurement, then we need a bigger ruler. We need distance so large that even light needs noticeable time. We need a clock that ticks with predictable rhythm. We need a setup that runs itself without relying on human reflexes. In other words, we need to use the sky. This is one of the most beautiful shifts in the history of science. When a measurement becomes impossible in a laboratory, the universe sometimes hands you a natural laboratory that has been running for billions of years. A system so vast and so regular that it can reveal what no hilltop experiment ever could. And the breakthrough came from an unexpected source, not a flash across Florence, but a tiny moving shadow out near the largest planet in our solar system. The moons of Jupiter were about to become the most precise stopwatch humanity had ever seen. When you cannot measure something on Earth, you either give up or you steal a clock from the heavens. Jupiter is the kind of planet that practically begs you to pay attention. It is huge, bright, impossible to miss, and surrounded by a little family of moons that swing around it with steady rhythm. In the 17th century, astronomers became especially interested in one moon named Io. Io regularly slips into Jupiter's shadow, disappearing like a tiny bead of light getting switched off, then reappearing again. These events happen with such dependable timing that people began treating them like celestial appointments. If you could predict them accurately, you could use them for navigation and for testing your understanding of planetary motion. And then something strange started to show up in the timing. An eclipse that should have happened at a particular moment sometimes seemed early and sometimes seemed late, not by a second or two, by amounts that made astronomers uncomfortable. If the moons of Jupiter were reliable, then why was the schedule wobbling? This is where Ole Christensen Romer enters the story, a Danish astronomer working in Paris. He was not staring at Jupiter hoping to be surprised. He was doing careful, almost patient bookkeeping. He compared predicted eclipse times to observed eclipse times over and over, and he noticed a pattern that did not behave like random error. When Earth was moving toward Jupiter in its orbit, the eclipses tended to show up earlier than expected. When Earth was moving away from Jupiter, the eclipses tended to show up later than expected. That pattern is a clue shaped like a hammer. Think about it in human terms. A friend across a long field is using a flashlight to signal you. When they flash the light, you see it. If you start walking toward them, the distance the light has to cross gets shorter. If you start walking away, the distance gets longer. If the light took no time at all, none of this would matter. You would see the flash the instant it happened, no matter what you were doing. But if light has a travel time, even a small one, then distance changes will show up as timing changes. A signal sent from farther away arrives later. A signal sent from closer arrives sooner. Romer realized he was not watching Jupiter's moons misbehave. He was watching light behave. He was watching a universal delay accumulate because the distance between Earth and Jupiter was changing as both worlds moved. When Earth was closer, there was less distance for the light to cross, so the eclipses seemed to happen sooner. When Earth was farther, there was more distance, so the eclipses seemed to happen later. That sounds obvious now, but at the time it was audacious. It meant the old assumption was wrong. Light was not instantaneous. It was fast, but it was a traveller. Romer did something bold with this realization. He made a prediction in public. He told the Academy of Sciences that a coming eclipse of Io would occur about 10 minutes later than the standard tables predicted. That is the kind of statement that either makes you famous or makes you a cautionary tale, because nature does not care about your pride. The sky will do what it does, and everyone will see whether you are right. So astronomers watched and waited, and the eclipse arrived late, right on Romer's schedule. That moment matters because it is one of the first times in human history that a deep truth was not merely argued, but pinned down by prediction. Romer had turned the sky into an experiment. He did not just claim light took time. He showed that if light took time, then the universe should behave in a particular way on a particular date, and it did. From those observations, Romer estimated that light takes about 22 minutes to cross the diameter of Earth's orbit. His number was not perfect, partly because the size of Earth's orbit was not known with the precision we have today, but the philosophical damage was permanent. Aristotle's confident instant light was gone. Light did not arrive. Light travelled. Once that door opened, it never closed again. After Romer, the speed of light was not a mystical idea. It was a measurable property of nature. But science is greedy in the best way. A single line of evidence is exciting, yet scientists always hunger for independent confirmation. If this was real, it should show up somewhere else, in a different kind of observation, for a different reason. That next confirmation came from a phenomenon with a wonderfully slippery name: stellar aberration. In the early 18th century, an English astronomer named James Bradley was searching for something else entirely. He was looking for signs of stellar parallax, the tiny shift in star positions that should occur as Earth orbits the Sun. It was a hard measurement, and at the time it had not yet been directly observed. What Bradley found instead looked like stars were shifting in the sky in a way that did not match the pattern he expected. The shift was small but consistent, and it repeated with the year. Then the explanation hit him in a way that feels almost too perfect. The story goes that he had the insight while on a boat, noticing how the direction of the wind seemed different depending on the boat's motion. Even if the wind itself did not change, your movement changes the angle the wind appears to come from. You have probably felt a version of this without thinking. Walk in still air, and it feels calm. Run in that same air and suddenly you feel a breeze in your face. You did not create wind in the world. You created wind relative to you. Rain gives the most intuitive picture. If rain falls straight down and you stand still, it hits the top of your head. But if you start running, you have to tilt your umbrella forward. The raindrops are still falling vertically, yet relative to your motion, they seem to come at you from an angle. Bradley realized starlight behaves the same way. Light from a distant star arrives at Earth moving at the speed of light. Meanwhile, Earth is moving along its orbit. Because of that motion, the telescope has to be angled slightly into the direction of Earth's travel to catch the incoming light, just like tilting an umbrella forward while running. The result is that the star appears slightly displaced from where you would expect it to be if Earth were not moving. That tiny displacement is stellar aberration, and here is the beautiful part. The amount of displacement depends on two speeds, the speed of Earth in its orbit and the speed of light. We can measure the angle of the aberration, and we can know Earth's orbital speed, which means we can solve for the speed of light. So Bradley did, and his results supported the same conclusion Romer had pulled from Jupiter's moons. Light is unimaginably fast yet finite. It has a fixed speed that leaves fingerprints all over the universe. By this point, the old instant light story had nowhere to hide. The sky itself had betrayed it twice in two different ways, but a new frustration appeared because even if you accept that light has a speed, you still want to grab that speed in your hands. You want to measure it directly here on Earth, not by watching moons and stars, but with an experiment you can build, repeat, and refine. That hunger leads to the next stage of the story, where scientists stop relying on celestial events and start building machines designed to race light across known distances. And that is where the measurements start getting sharp enough to change the entire foundation of physics. There is a particular kind of satisfaction in science, when a truth stops being something you infer from the sky and becomes something you can demonstrate on a tabletop. Romer and Bradley had done the universe a favor. They proved light was not instantaneous, but their measurements still felt like reading a secret message written in distant shadows and tiny angles. Naturally, the next question was almost personal. Can we measure the speed of light directly, here on Earth, with equipment we can build and repeat? Can we turn a cosmic constant into a laboratory number? That demand is not just curiosity, it is a change in attitude. The moment you can repeat a measurement whenever you want, you stop treating it like a special event and start treating it like a property, like the density of water, or the boiling point of a liquid, or the pitch of a tuning fork. Something that belongs to the world, not just to the heavens. The problem was still the same. Light is fast, so fast that even if you send it across a city and back, the round trip is far shorter than the blink of an eye. A human hand cannot open and close a shutter precisely enough. A stopwatch cannot resolve a few millionths of a second. If you want to catch light, you need a machine that can outrun human reflexes. This is where 19th century physics begins to feel like engineering art. Armand Fizeau designed a method that sounds almost like a magic trick, but it is pure logic. He sent a beam of light through the gaps of a rapidly spinning toothed wheel, across a long distance toward a mirror. The mirror bounced the beam back along the same path. The returning light then tried to pass back through the wheel to reach the observer. Now comes the clever part. If the wheel is rotating slowly, the returning beam finds the same gap it left through, and you see it. If the wheel is rotating at a certain faster rate, the returning beam arrives at the exact moment a tooth has moved into that gap, and the beam is blocked. The light disappears. So Fizeau could turn the wheel speed up and find the point where the returning light was extinguished. That extinction point is a timing marker created by the wheel itself, not by a human hand. If you know the distance to the mirror, and you know how fast the wheel rotates, you can calculate how long the light took to travel out and back, and from that, you get the speed. In a sense, the wheel becomes a mechanical stopwatch that is fast enough to measure something your nervous system cannot. It is one of those moments where the human body is no longer the limiting instrument. The machine takes over. Fizeau set his apparatus across a long baseline, on the order of several kilometers, and pulled a number out of the setup that matched the astronomical measurements surprisingly well. Not perfectly, but close enough to make the point undeniable. You could measure the speed of a light without needing Jupiter, without needing stars, without needing the patient accumulation of months of observations. You could do it on demand. That changed everything. Because once you can measure something, you can measure it again, and then you can improve. You can make the baseline longer, you can reduce vibrations, you can refine the wheel, you can chase sources of error, you can start turning a rough estimate into a precision constant. And that hunger for precision is not just about the joy of getting more digits. Precision has a habit of revealing deeper problems. When your measurements get sharp enough, small discrepancies stop being noise and start being clues. Soon after, Léon Foucault introduced a different approach that would prove even more powerful. Instead of a toothed wheel, he used a rotating mirror. The idea is elegant. A beam of light travels to a distant mirror and returns. But while the light is in flight, a mirror in the apparatus rotates a tiny amount. Because the mirror has turned, the returning beam is deflected slightly, landing at a different position than it would have if the mirror were stationary. That tiny shift is measurable, and that shift is directly tied to the travel time of the light. Because the faster the light returns, the less the mirror has time to rotate, and the smaller the shift. The slower the light returns, the more the mirror turns, and the larger the shift. So once again, you replace a human timing problem with a geometric measurement. You convert time into a distance on a scale, something your eyes and instruments can resolve with far more precision. Foucault's method did more than refine a number. It also helped settle an argument about how light behaves in different media. By sending light through air and then through water, the experiments could test whether the speed increased or decreased in denser materials. The results supported the view that light slows down in denser media, which aligned beautifully with the wave theory of light and strengthened the overall framework that physics was building at the time. But there is a subtle twist hiding inside all this progress. When you measure the speed of light more and more accurately, you begin to notice how strangely stable it is. Every refinement, every new technique, every improved instrument keeps pointing back to the same reality. Light has a fixed speed in vacuum. It does not seem to depend on the motion of the source in any simple way. It does not behave like a thrown ball, where you add the speed of the throw to the speed of the runner. That is the kind of detail you can ignore when your measurements are crude. But once you can measure with confidence, the constancy starts to feel eerie, and the implications creep in. Because in the physics of that era, there was an expectation that waves needed a medium. Sound needs air. Water waves need water. So if light is a wave, it should need something too. That imagined something was called the ether, a subtle, invisible substance that was supposed to fill space and carry light waves the way air carries sound. If the ether existed, then Earth should be moving through it, like a ship moving through an ocean. And if Earth is moving through the ether, then the measured speed of light might differ depending on direction. Light traveling with the ether wind should appear to go faster than light traveling against it, at least in the simple picture. That is the kind of prediction you can only seriously test once you have laboratory control and high precision. Which is exactly what these new measurement techniques were making possible. So this part of the story is not just about clever devices and sharper numbers, it is about setting a trap for reality. Fizeau and Foucault helped transform the speed of light from an astronomical curiosity into a laboratory constant. And that achievement did something dangerous. It made scientists confident enough to ask a new question, one that would end up detonating the old understanding of space itself. If light is a wave, what is it waving through? And if there is an ether, can we detect Earth's motion through it by measuring light speed in different directions? In the next part, we walk into the most famous null result in the history of science. An experiment that was supposed to find the ether wind and instead found nothing, and that nothing was louder than anyone expected. Once you accept that light is a wave, a new question creeps in like a splinter you cannot ignore. Waves usually need something to ripple through. Sound needs air. Ocean waves need water. Even a vibrating guitar string needs a string. So in the late 19th century, it felt almost unavoidable to imagine that light waves also needed a medium. physicists gave that invisible medium a name: the luminiferous ether. The idea was that all of space was filled with this substance, weightless, transparent, everywhere, and somehow perfect at its job. It had to be stiff enough to carry extremely fast waves, yet so ghost-like that planets could move through it without feeling resistance. It had to be everything and nothing at the same time. That kind of thing should make you suspicious. Whenever an idea is designed to explain everything while refusing to be detected by anything, it starts to smell like a patch. But science does not kill an idea because it smells weird. Science kills an idea when it fails a test, and the ether came with a testable prediction. If the ether is real, and Earth is moving through it as we orbit the Sun, then there should be an ether wind, like the headwind you feel when you stick your hand out of a car window. A beam of light traveling in the direction of Earth's motion should be slightly slowed relative to the ether, and a beam traveling against Earth's motion should be slightly sped up relative to the ether. Light traveling perpendicular to Earth's motion should behave differently again. The effect would be small because light is absurdly fast, but it should be there. And by the 1880s, physicists finally had the precision tools to go looking. This is where the story tightens into a classic scientific thriller. Two men, a delicate machine, and a prediction that seems almost too clean. In 1887, Albert Michelson teamed up with Edward Morley to build an instrument designed for one job: detect Earth's motion through the ether by detecting tiny differences in the speed of light depending on direction. Their device was an interferometer, which is a fancy word for something with a simple idea. Split a beam of light into two paths at right angles. Send those two beams down different corridors. Bounce them back with mirrors. Recombine them. If one beam takes even a tiny fraction of a second longer than the other, the recombined light will show an interference pattern, a set of bright and dark fringes that shifts when the travel times change. That is the beauty of the method. You're not trying to time light with a stopwatch. You're letting light compare itself to itself. And light is far more honest about timing than our hands and eyes will ever be. Michelson and Morley made the paths effectively long by using multiple mirrors, creating an optical distance on the order of dozens of feet, achieved through a careful arrangement of many reflections. They used monochromatic yellow light because a clean single color makes the fringe pattern sharp and easier to measure. Then they did the obvious thing. They rotated the entire apparatus. If there is an ether wind, turning the device should change which arm is aligned with that wind, and the interference fringes should slide back and forth as the travel time difference changes. They even had a predicted size for the effect. The expected shift was on the order of a fraction of a fringe, around 4/10 of a fringe, not huge but clearly measurable with a careful setup. So they watched, and nothing happened. Not nothing as in a messy result. Not nothing as in too much noise. The fringes stayed stubbornly still, far smaller than predicted, less than 1/40th of what they expected. In other words, the ether wind was either not there, or it was hiding with supernatural skill. They repeated the experiment, they refined it, they ran it again. The result remained the same. Light traveled at the same speed in every direction, regardless of Earth's motion through space, regardless of how the apparatus was oriented. This is why the Michelson-Morley experiment is often called the most famous failed experiment in history. It did not fail because it was sloppy. It failed because nature refused to cooperate with the theory. And when a careful experiment refuses to cooperate, the theory is the thing in trouble. Now here is the psychological twist. A null result is not satisfying in the moment. It gives you no neat new number, no triumphant confirmation, no clean mechanism to point to. It feels like staring into a locked door. But it was precisely that locked door that forced physics to evolve. Because the experiment did not simply say we cannot find the ether. It suggested something more disturbing. Maybe the ether does not exist, or maybe our whole picture of motion and space is wrong. Either way, the foundation started to wobble. Michelson, the man at the center of this, carried that weight. The preparation and the pressure around this work were intense enough that it left marks on him as a human being, not just as a scientist. And yet the work mattered so much that his career still became historic. He would eventually become the first American to win the Nobel Prize in any science. But the real consequence of the experiment was not a medal. It was a puzzle with teeth. If there is no ether wind, then how can light have a fixed speed? In the everyday world, if you run toward a thrown ball, it hits you faster. If you run away, it hits you slower. That is how speeds behave. You add and subtract. Yet light refused to play that game. Physicists tried all kinds of patches. Maybe the ether is dragged along with Earth. Maybe the apparatus physically shrinks in the direction of motion in just the right way to cancel the expected shift. People proposed ideas that sounded crazy until you realize they were cornered by the data. And then, in a move that would have sounded like cheating to earlier generations, the story takes a strange turn in the modern era. After centuries of trying to measure the speed of light more precisely, scientists eventually decided to flip the problem. Instead of treating the speed of light as a quantity we measure, they treated it as a fixed definition. In the early 1980s, an international standards body defined the speed of light in a vacuum to be exact, with zero uncertainty, and then used that to define the meter in terms of how far light travels in a tiny fraction of a second. That sounds like a trick until you understand what it really means. We built our measurement system around a constant that nature seems to enforce everywhere. We stopped chasing the number and instead anchored our rulers to it. And yet the core mystery remained. The Michelson-Morley result was not just a dead end. It was a signpost. It pointed to an answer that would feel almost impossible when first spoken out loud. If the speed of light is the same for everyone, then it is not the speed of light that changes when you move. It is you. It is your time. It is your space. In the next part, we meet the person who took that locked door and kicked it open, not with better mirrors, but with a more ruthless idea. After Michelson and Morley, physics found itself in an awkward position. The ether was supposed to be the invisible ocean that carried light waves, and Earth was supposed to be the ship cutting through it. The experiment was built to detect that motion, and the universe answered with silence. A lot of brilliant minds did what humans always do when reality refuses to cooperate. They tried to save the old picture with careful patches. Maybe the ether was being dragged along with Earth. Maybe matter physically contracts in the direction of motion in just the right way to hide the ether wind. Maybe time itself shifts a little in moving systems, not because time is strange, but because the ether messes with the way clocks work. Those ideas were not foolish. They were attempts to respect the data without throwing away an entire worldview. Hendrik Lorentz, for example, worked out a mathematical framework where moving objects could shrink and moving clocks could offset in a way that made the ether undetectable. The math could be made to fit. But the story underneath the math was still haunted. It still treated the ether as the true stage of reality, and everything else as a kind of distortion. Then a young man showed up and did something that sounds simple, until you realize how ruthless it is. He removed the ether entirely. Albert Einstein was not a university professor when he made his move. He was working a day job at a patent office in Switzerland, reading inventions, evaluating claims, thinking about how machines and signals actually behave. In that environment, you develop a certain intolerance for hidden assumptions. You start asking questions like, what do we really measure? What do we really know? And what are we merely imagining because it makes us comfortable? Einstein also carried a private obsession that had been gnawing at him since he was a teenager. Imagine you are 16 years old and you decide to chase a beam of light, not metaphorically, literally. You run alongside it at the speed of a light and you look over. What should you see? If you use the common sense physics of everyday life, The answer feels straightforward. If you match the light's speed, then relative to you, the wave should freeze in place, like a rippling pattern that stops moving. A stationary wave in space just hanging there. But that picture clashes with something deeper. James Clerk Maxwell's equations of electromagnetism did not allow for a frozen light wave in empty space. They predicted electromagnetic waves that travel at a fixed speed, always. The math did not care whether you were chasing the beam. It insisted the wave should still move. So which rule do you trust? The rule that says speeds add the way you expect, or the rule that says light does not negotiate its speed? Einstein eventually realized the mistake was not in the light. It was in the way we were trying to combine motion and time. In 1905, he built what we now call special relativity on two postulates, two statements he chose to treat as foundational. The first one sounds almost boring, which is exactly why it is powerful. The laws of physics are the same in all inertial reference frames. Inertial just means not accelerating. If you are in a smoothly moving train with no bumps and no turns, there is no experiment you can do inside that train that will prove you are moving at a constant speed. You can drop a ball, it falls straight down. You can pour a drink, it pours normally. You can play catch, and the ball behaves the same way it would if you were standing still. Motion at constant velocity is relative. There is no absolute state of rest written into the universe that you can detect from within. That principle was not entirely new. It had roots going back to Galileo. But Einstein paired it with a second postulate that was explosive. The speed of light in a vacuum is the same for all observers in inertial motion, regardless of how the source is moving, and regardless of how the observer is moving. Let that land for a second, because it is the moment your intuition starts sweating. If you are on a train moving forward and you shine a flashlight toward the front of the train, common sense says the light should move faster relative to someone standing on the platform. After all, the train is already moving, and you are launching the light forward from a moving source. That is how a thrown ball works. That is how almost everything works at human speeds. But Einstein's postulate says no. The person on the platform and the person on the train both measure the exact same speed for the light. So how can both be right? For a moment it feels like the universe is playing word games, but it is not. It is forcing a trade. If the speed of light refuses to change, then the measurements of time and space must adjust in a very particular way to keep the rule intact. This is the heart of special relativity. It does not ask you to believe in magic. It asks you to accept that time and space are not rigid backdrops. They are flexible ingredients, and their flexibility is exactly what prevents contradictions. Suddenly, the Lorentz-style patches become something else entirely. What looked like a weird distortion caused by motion through an ether becomes a direct description of how reality works without any ether at all. Length contraction is not a trick that hides an ether wind. Time dilation is not an instrument error. They are the universe balancing its own equations. And here is the part that makes Einstein's move feel dangerous even now. Once you accept these postulates, you do not get to keep a single universal clock that everyone shares. You do not get to keep a single universal definition of what counts as simultaneous. The phrase at the same time becomes local. It depends on motion. It depends on the observer. Not because truth is subjective, but because time itself is stitched into the structure of motion. Einstein did not stop there. In that same miraculous year, he also connected energy and mass in a way that would reshape the 20th century. He showed that mass is a form of energy, and that energy behaves like mass in how it resists acceleration. In other words, mass and energy are two faces of the same bookkeeping system. That idea will matter later when we talk about why pushing objects close to light speed becomes brutally expensive. But for now, the main shock is simpler: shock. Einstein took the locked door left by Michelson and Morley, and instead of trying to pick the lock, he changed the building. He said there is no hidden ether. There is no preferred cosmic rest frame. There is only the rule that light speed is constant, and the consequence that time and space must bend themselves to make that rule true. And in the next part, we finally pay the bill. Because the first payment is time. If you move fast enough, your clock does not just seem to run slow, it runs slow. The easiest way to misunderstand time dilation is to treat it like a visual illusion, like a trick of perspective. Something you only notice because you are comparing two moving things and your brain gets confused. That would be comforting, because it would mean time itself stays normal and only your measurements get weird. But special relativity does not let you keep that comfort. If the speed of light is the same for everyone, then moving through space changes how you move through time. Not in a poetic way, in a mechanical, unavoidable way. A moving clock does not just look slow, it runs slow, and the slower running is not a flaw in the clock. It is the universe doing bookkeeping. So let's build the simplest clock you can imagine, one that does not depend on gears or springs or chemistry. A light clock. Picture two mirrors facing each other, a fixed distance apart with a pulse of light bouncing between them. Every time the light hits the top mirror and returns to the bottom mirror, we count one tick. If you're sitting next to this clock, at rest relative to it, the light goes straight up and straight down. The distance is simple, the path is simple, the tick rate is steady. Now slide the entire clock sideways, fast, while you stand still and watch it pass. From your perspective, the light inside the clock cannot travel straight up and down anymore. Because while the light is moving upward, the clock is also moving sideways, so the light has to chase the moving mirror. The path becomes diagonal on the way up and diagonal on the way down, like a zigzag. Here is the trap that closes around your intuition. The speed of that light is still the speed of light. It does not speed up just because the clock is moving. It does not slow down just because you are watching. It stays fixed. So if the light speed stays fixed and its path is longer, then the light must take more time to complete a tick. There is no escape hatch. Longer path at the same speed means longer travel time. That means each tick takes longer from your point of view. So the moving clock runs slow. At this point, you might try to save your instincts by saying, "Fine, the moving clock looks slow to me, but maybe my clock looks slow to the person riding with it." Maybe it is just symmetrical, a disagreement in measurement, not a real change. And yes, there is symmetry in how observers describe each other while they are moving smoothly. Each observer can say the other clock is running slow. That is one of the strangest parts of relativity, and it is real. But the universe has a way of cashing out abstract symmetry into a concrete comparison. You bring the clocks back together, you put them side by side again, you ask which one experienced more time. And that question has a sharp answer. The way to feel this is through the famous twin paradox. Imagine two twins standing next to each other on Earth. One stays home. The other boards a spaceship, travels to a distant star at extremely high speed, turns around, and comes back. When they reunite, the traveling twin is younger than the stay-at-home twin. Not younger in spirit, younger in biology. Fewer heartbeats, fewer cell divisions, less elapsed time in their body. This is the part where people often protest, because it sounds like a logic error. If motion is relative, why cannot each twin claim the other was moving, therefore the other should age less? The key is hiding in plain sight. The traveling twin does not stay in one smooth motion the entire time. They leave Earth, they change direction, and they come back. That change in direction requires acceleration, and acceleration means they do not remain in a single inertial reference frame. Meanwhile, the stay-at-home twin remains, to a good approximation, in one inertial frame for the whole story. They do not switch frames the way the traveler does. They do not flip their notion of what counts as simultaneous across the universe. The traveler does. When the ship turns around, the traveler's frame changes, and with it, their slice of what they consider happening right now at distant locations changes too. That shift is not philosophical. It is the geometry of space-time doing exactly what it must do to keep the speed of light consistent. So the paradox dissolves because the two journeys through space-time are not the same kind of journey. One twin follows a path that is more straight in space-time, the other follows a path that bends, switches frames, and reconnects. When you compare the total time experienced along those two different paths, the stay-at-home path contains more time. Another way to say it, without turning this into a math lecture, is that you cannot decide who aged less until the twins meet again at the same place. While they're separated, each has their own perfectly valid description of the other. But reunion forces a direct comparison, and the geometry chooses a winner. And that winner is not chosen by opinion. It is chosen by the structure of the universe. This is why time dilation is not merely a visual effect. It is not a quirk of the instruments. It is the same rule that makes the light clock tick slower from the outside view. The speed of light is fixed, so the relationship between space and time must flex, and the flex shows up as real differences in elapsed time when paths reconnect. Now, there is a subtle point people sometimes stumble on. Acceleration is not what causes time dilation in the basic sense. Even during the long cruise where the ship moves smoothly, time dilation is already happening relative to Earth. Acceleration simply breaks the symmetry and makes the reunion comparison unambiguous. It is the part of the story that prevents you from treating both perspectives as perfectly interchangeable from start to finish. So what does this mean for you, sitting on a couch, watching a video? It means time is not a universal river flowing at one rate everywhere. It is more like a landscape, where motion changes your route through it. At the speeds we normally live at, the difference is tiny, too small to feel. But tiny is not the same as imaginary. Tiny is just waiting for the right experiment, the right particle, the right precision clock. And there is one more sting in the tail. If time can stretch, space has to answer too. Because the universe is not going to let you break the speed of light by clever accounting. It will reshape lengths as well, squeezing distances in the direction of motion, so the overall structure stays consistent. In the next part, we follow that second payment, length contraction, and the brutal truth that the speed limit cannot be hacked. Not by engines, not by stacked speeds, not by any trick you can dream up. Time dilation is unsettling because it reaches into your life and touches your aging. But length contraction is unsettling for a different reason. It reaches into the shape of the world itself. It tells you that distance is not a fixed stage we move across. Distance is part of the deal. If you have been quietly hoping for a loophole, this is where the universe closes the door. Here is the temptation. If nothing can go faster than light, then maybe we can cheat by stacking speeds. Put a spaceship on a fast-moving platform, then fire a smaller ship forward from that ship, then fire a beam from that smaller ship. In everyday life, speeds add. A runner on a train can move faster than the train relative to the ground. Throw a ball forward on a moving bus and it goes faster relative to the street. So it is natural to ask, why not do that forever? Why not keep building a ladder of motion until we climb past the speed of light? Relativity answers with a calm, merciless no. Speeds do not add the way your instincts want them to add. At low speeds, the old rule is a good approximation. But as you get closer to light speed, the universe switches to a different accounting system, one designed to keep the speed of light fixed in every inertial frame. Instead of simply adding speeds, you get a combined speed that is always less than light speed, as long as each individual speed is less than light speed. The closer you start to the limit, the less you gain from adding another boost. It is not a softer limit you can overshoot by being clever. It's a hard limit built into the geometry. Let's make it concrete. Imagine a spaceship traveling at an extremely high speed relative to Earth. Inside that ship, an astronaut launches a smaller probe forward at another high speed relative to the ship. The astronaut measures the probe moving away at that speed. The people on Earth measure the ship moving away at its speed. So what does Earth measure for the probe? Your intuition says we add them and the probe becomes faster than light. But the universe refuses to let that happen. From Earth's view, the probe is faster than the ship, yes, but not by the full amount you would expect. The combination rule squeezes the total so it stays under the limit, and the reason it has to squeeze becomes obvious when you remember what we already paid in Part 7. Time dilation. If the ship's moving clock runs slow relative to Earth, then the astronaut's definition of 1 second is not matching Earth's definition of 1 second in a simple way. If you force speeds to add normally while time itself is shifting, you would end up with contradictions, including the ability to beat a light beam in some frames. So velocity addition is not a random adjustment, it is the universe staying consistent. Now length contraction enters like the final piece of a trap snapping shut. Go back to the light clock idea, but instead of a clock, think of a ruler. Imagine a spaceship with a known length, measured by the people inside it. They lay a ruler along the hallway, or they use a calibrated system of measurements, and they agree on the ship's length. Now you watch that ship fly past you at extremely high speed. Relativity says the ship's length along the direction of motion is shorter in your frame, not because it got squished by engine stress, not because it physically crumpled. It is shorter because the definition of measuring length depends on simultaneity, on which points you consider at the same time. To measure the length of a moving object, you have to record where its front and back are at the same moment in your frame. But we already know there is no universal now. Different frames slice space-time differently, so the set of events you call the front here now and the back here now is not the same set of events the astronaut calls front here now and back here now. That difference in simultaneity is what produces length contraction. From your view, the moving ship is shorter along its motion. From the ship's view, it is normal. Both descriptions are correct in their own frames, and neither can be declared the single true one because there is no preferred frame written into the universe. This is where the speed limit becomes unhackable. Because if you want to make an object reach light speed, you would need to accelerate it so much that time dilation becomes extreme, and length contraction becomes extreme, and the velocity addition rule keeps squeezing your gains. Each new push buys you less and less increase in speed relative to an outside observer. The closer you get, the more the universe pushes back. You can picture it like trying to reach the horizon by walking. You can keep walking forever, but the horizon keeps receding. Not because you are failing, but because you are chasing a boundary created by geometry. That is what light speed is like in relativity. It is a boundary in space-time, not a high score. Now it is tempting to say, fine, then from the ship's perspective we can still do it. If the ship keeps accelerating, maybe the ship will eventually see a beam of light crawling along slowly, so that in the ship's view the ship can catch it. But that is exactly what the postulate forbids. In every inertial frame, light moves at the same speed. You can accelerate all you want, but at any instant you can always imagine the ship as momentarily in a frame where the local physics works the same way, and in that moment the speed of light is still the speed of light. You do not approach the beam like a runner approaches a slower runner. You keep seeing it rush away at the same speed. So the limit holds from every angle, and now you can feel the deeper implication. The speed of light is not just the speed of light. It is the conversion factor between space and time. It tells you how much time corresponds to how much distance in the structure of space-time. That is why changing one forces changes in the other. That is why the universe protects the constant so fiercely. We have now met two of the big consequences, time dilation and length contraction. Together they reshape how we think about motion. But there is a third consequence that is even more emotionally disruptive because it attacks a word you use every day without thinking, now. In the next part, we're going to break the idea of a universal present, and once you see how that breaks, you will understand why faster-than-light messaging is not just difficult. It is logically poisonous. There is a word you use every day that special relativity quietly sabotages. Now. You think you know what it means. Right now means this exact moment. It feels like a single spotlight sweeping across the universe, illuminating one thin slice of reality at a time. Your brain treats the present like a cosmic layer cake, and we're all standing on the same layer together. That picture is so natural that it feels almost rude to question it. But it is also built on an assumption that only works in a universe where information can travel instantly. And we do not live in that universe. The moment you accept a maximum speed for signals, you inherit a problem. How do you decide what counts as happening at the same time in two different places? It sounds like a philosophical question, but it becomes practical the moment you try to synchronize clocks. Imagine you and I are far apart, and we want our clocks to agree. We can try to do it the obvious way. We can set them together, then separate. But separating takes time and motion is exactly the thing that messes with time. So instead, we try a different plan. We use light signals. I send a flash to you. You receive it and immediately send a flash back. I measure the total round-trip time. Then I assume the light took half the time to go to you and half the time to come back. With that assumption, I can assign a time to the moment you received my first signal. That is the basic logic behind how you might build a shared time system across distance. It feels harmless. It feels like common sense. But notice what just happened. The definition of simultaneous now depends on a convention. It depends on assuming the signal took equal time in each direction. And that assumption depends on the speed of light being the same in all directions in your frame. Now add motion. Imagine two people in two different moving systems, each trying to synchronize clocks using their own signals. Each of them has a perfectly consistent method in their own world. Each of them trusts their own rulers and clocks. Each of them insists light moves at the same speed in their frame. And here is the twist. When they compare notes, they do not agree on what events are simultaneous. This is not because one of them is wrong. It is because simultaneity is not a universal feature of reality. It is a relationship that depends on motion. To feel this in your bones, picture a long train moving smoothly past a platform. There is a person standing in the middle of the train, and there is another person standing on the platform as the train passes. Now imagine two lightning bolts strike. One hits the front of the train, the other hits the back of the train. Let's set it up so that in the platform frame the strikes happen at the same time. The flashes race toward the middle of the train. The person on the platform is standing still relative to the ground. If the strikes were truly simultaneous in that frame, the light from the front and the light from the back should reach the platform observer at the same moment, because the observer is equally distant from both strike points if we arrange it that way. But the person in the middle of the train is moving. They are moving toward the location where the front strike happened, and moving away from the location where the back strike happened. Light always moves at the same speed, so the flash from the front has a shorter chase and reaches the train observer sooner. The flash from the back has a longer chase and reaches the train observer later. So the train observer receives the front flash first. Now comes the dangerous question. If you receive one flash first, does that mean that strike happened first? In everyday life, yes. But in relativity, you have to be careful. Signal arrival order can be influenced by motion and distance. So the correct approach is to ask how each observer defines simultaneous time across space, using their synchronized clocks. And when you do that, the result is unavoidable. In the platform frame, the strikes were simultaneous. In the train frame, they were not. In the train frame, the front strike happened before the back strike. Two observers, both correct, both obeying the same laws of physics, disagreeing about the order of events. That sentence should make your stomach drop a little, because it sounds like reality has become subjective, but it has not. What has changed is what you are allowed to call objective. There are still things everyone agrees on, If one event can physically cause another, their order is locked. If I throw a ball and it breaks a window, no observer can claim the window broke before I threw the ball, because the cause must come before the effect when the influence travels at or below light speed. But for events that are too far apart and too close in time for any signal, traveling at or below light speed to connect them, the universe does not enforce a single order. There is no causal link to preserve, so different frames can slice the story differently. This is the deep meaning behind the idea that there is no universal now. The universe is not giving you one global present moment that everyone shares. It gives you local presence, tied to your state of motion, and stitched together by signals that cannot exceed the cosmic speed limit. So when you say, right now a star is exploding somewhere, you are smuggling in a hidden assumption. Which right now? Right now, according to whom? Right now on what moving platform of clocks? At human scales, this feels like pointless hair splitting, because the differences are tiny. But the logic is not tiny. The logic is absolute, and it becomes crucial the moment you start imagining faster than light travel or faster than light communication. Because if there is no universal now, then a faster than light message is not just a message that arrives quickly. It is a message that can arrive in a different order depending on who is moving. It can become a message that arrives before it was sent, in some frames. That is when the universe stops being merely weird and starts being unstable. This is why relativity of simultaneity is not a cute brain teaser. It is the key that connects the speed limit to causality. It tells you that the speed of light is not only about travel time, it is about preserving the logical structure of reality. In the next part, we take this idea and draw its boundaries. We build the map that shows what can influence what can never influence what, and why trying to outrun light does not just break rules. It breaks the order of cause and effect itself. By now it should feel obvious that the speed of light is not only about light, it is the universe's rule for how fast reality can spread news about itself. And once you accept that, you stop thinking of time and space as separate things. You start thinking of them as one connected structure, where distance and duration trade off against each other. There is a line from the early days of relativity that captures this shift perfectly. Space by itself and time by itself are doomed to fade into mere shadows, and only a kind of union of the two preserves an independent reality. That is not just poetic, it is the mental flip that lets the rest of this make sense. So let's build a picture you can hold in your head. Imagine a single event, right here, right now. A camera flash goes off. The moment the flash happens, the light begins expanding outward in every direction. 1 second later, the light has reached everything 1 light second away. 2 seconds later, it has reached everything 2 light seconds away. The light keeps going, and it draws a boundary as it goes. If you were to sketch this on a spacetime map, it would look like a cone. The flash event sits at the tip. The expanding wave of light traces the surface of the cone as time moves forward. That shape is called the light cone, and it is one of the cleanest ways to see what can influence what. Everything inside the forward light cone is reachable by signals that travel at or below light speed. That means those events could be caused by the flash. You could shine the flash, and then later, inside that cone, someone could receive it, react to it, build a detector that triggers from it, or get scared by it and spill coffee. Those later events are in the flash's causal future. Now flip the story. Imagine running time backward. If we keep following light paths backward, we get a second cone opening into the past. Everything inside that backward cone represents events that could have influenced the flash. A power surge, a finger pressing a button, a battery being installed yesterday, a star exploding long ago that eventually triggered a chain of decisions that put you in this room holding a camera. Those are in the flash's causal past. This is where the map becomes brutally useful. There is a third region, everything outside the light cones. Events out there are too far away in space and too close in time to be reached by any signal that obeys the speed limit. No light beam from the flash can get there in time. No slower signal can either, and nothing out there could have sent a signal that reaches the flash event. There is no possible cause and effect connection, not because we lack technology, but because the geometry forbids it. That outside region has a strange consequence. Since there is no causal link, the universe does not need to protect a single event order for those happenings. Different observers moving relative to each other can disagree on which of two outside events happened first, and the disagreement does not break anything. It does not break anything because the events cannot affect each other anyway. This is the missing bridge between the death of a universal now and the protection of causality. If two events are inside each other's light cones, their order is locked. Cause must come before effect, because any influence has to travel at or below light speed. But if two events are outside each other's light cones, their order is not a universal fact. It is frame dependent, and that is allowed because no influence can pass between them. Now you can see why faster than light signaling is radioactive. Imagine you and a friend are separated by a huge distance, maybe across the galaxy. Under normal physics, any message you send takes years to arrive. But suppose you have a magical communicator that can transmit faster than light. You send a message, and your friend receives it almost instantly. At first, this sounds like a simple upgrade: faster delivery, better conversations, less waiting. But look at the light cone map. If the signal outruns light, it can land outside your forward light cone, because it reaches a far place too quickly. That means the receiver event can be space-like separated from the sending event. And space-like separated events have a frame-dependent order. So there will exist some observers, moving relative to you, who say the receive event happened before the send event, not because they are mistaken, but because their slice of simultaneity tilts differently through space-time. The signal itself has created a situation where effect can appear before cause in some frames. If that were the end of the story, you might try to shrug it off. Maybe it is only a weird bookkeeping artifact. Maybe nobody can exploit it. But now add the simplest possible response. Your friend replies using the same faster-than-light method. They send a message back. You have just built a loop. In some frames, the reply can arrive at your location before you sent the original message. You can literally receive an answer to a question you have not asked yet. That is not a cute time travel story. It is a logical contradiction engine. Because once you can send information into your own past, you can start building messages that cancel their own causes. You can send a warning that prevents itself from being sent. You can send a decision that erases the reason for the decision. The system collapses into paradoxes where the universe cannot consistently decide what happens. This is why the speed limit is not just a practical barrier. It is a structural barrier that protects logic itself. The light cone is the fence around causality. Faster than light travel or communication is not merely hard, it is the kind of thing that would punch holes in the fence. So when relativity insists that nothing carrying information can outrun light, it is not being stubborn. It is keeping the universe from turning into a self-contradictory mess. And here is the moment where healthy skepticism should kick in. Everything we have discussed so far can sound like an elaborate theoretical castle built from a single postulate. Beautiful, yes. Weird, yes. But how do we know it is true in the physical world? In the next part, we leave thought experiments behind and walk through the reality checks. The experiments that keep passing, the clocks that keep disagreeing exactly the way relativity predicts, the particles that should die and do not, and the modern technology that would quietly fail if time and space were not playing by these rules. So how do we know any of this is real? Not just clever math, not just a beautiful story that happens to fit a few famous experiments. How do we know time actually slows, and space actually reshapes, and the universe really does enforce that speed limit the way we have been describing? The answer is that we stopped asking the universe politely. We started interrogating it with clocks, particles, and machines that do not care about our instincts. And the universe has been giving the same answer over and over with the kind of consistency that slowly kills doubt. One of the cleanest tests is also one of the most satisfying. Take the twin paradox and make it literal. Not with spaceships, but with the kind of travel humans already do. In the early 1970s, researchers working with the United States Naval Observatory took extremely precise atomic clocks and put them on commercial airplanes. They flew the clocks around the world. They did it in both directions, eastward and westward, because direction matters once you remember Earth itself is rotating. Why both directions? Because if you fly eastward, you are moving with Earth's rotation, which changes your effective speed relative to the center of Earth. If you fly westward, you are moving against that rotation. You're still in an airplane either way, but the universe does not care about your seatbelt. It cares about your velocity through space-time. There is another wrinkle too. Airplanes fly high, and higher altitude means slightly weaker gravity than on the ground. In Einstein's later theory, clocks in weaker gravity tick faster, so the flying clocks are being tugged in two directions. Special relativity says motion makes them tick slower. General relativity says weaker gravity makes them tick faster. That combination sounds messy, but it is exactly the kind of messy the universe is good at, because the predictions are still precise. When you account for the speed and the altitude and the flight path, you can predict how much the airborne clocks should gain or lose relative to clocks kept on the ground, and the results matched. The eastward flying clocks ended up slightly behind the ground clocks, on the order of tens of nanoseconds. The westward flying clocks ended up ahead, on the order of a few hundred nanoseconds. Those are tiny differences, but they are not noise. They are the fingerprints of relativity on a human scale, published and repeatable, a macroscopic demonstration that moving clocks really do run slow. If that feels too delicate, the universe offers a more dramatic demonstration that happens above your head every day, whether you care or not. Cosmic rays slam into the upper atmosphere and create showers of particles. Among them are muons, unstable particles that behave like heavier cousins of the electron. In laboratory conditions, a muon at rest lasts only about 2.2 microseconds before it decays. That is a few millionths of a second. On paper, that is not enough time for a muon to travel very far, even moving near the speed of light. You would expect most of them to vanish long before reaching the ground, and yet detectors at Earth's surface register muons in large numbers. Something has to give. Either we have misunderstood how muons behave, or time is doing what relativity says it does. From our point of view, the answer is time dilation. Those muons are moving extremely fast relative to Earth, so their internal clocks are running slow relative to us. What looks like 2 microseconds in the muon's rest frame becomes many more microseconds in our frame, enough time for a large fraction of them to survive the trip through the atmosphere and reach the ground. Now here is the beautiful part. From the muon's point of view, it is not their clock that is slow. Their clock feels normal. Instead, the atmosphere is the thing that changes. The distance to the ground is length contracted. The whole layer of air they have to cross is squashed in the direction of motion, making the trip short enough to complete within their normal lifetime. Two different stories, same physical outcome. The kind of agreement you do not get from a coincidence. You get it from a structure. If you want this pushed into the extreme, we can do that too. We can trap particles in circles and make them live inside relativity for hours. In the 1970s, researchers at the European Organization for Nuclear Research, also called CERN, accelerated muons in a storage ring until they were moving so close to light speed that their time dilation factor was enormous, around 29. They then measured how long the muons lasted. The observed lifetime matched the predicted time dilation with striking precision, and there is a crucial lesson tucked inside that result. The muons in the ring are undergoing intense acceleration all the time because they are constantly being forced to change direction. If acceleration itself were the thing that slowed time, the predictions would fail, but they do not. The measurements agree with the idea that it is velocity that drives time dilation. Acceleration changes frames and makes reunions unambiguous, but it is not the secret ingredient that makes clocks slow. The slow ticking is built into motion through space-time. At this point, you might be thinking, okay, clever experiments, interesting particles, still a little distant from everyday life, so let's bring it all the way into your pocket. Every time you navigate with the global positioning system, you are trusting relativity whether you know it or not. Your phone receives timing signals from satellites. It uses the difference in arrival times to compute your position. That only works if the timing is brutally accurate, because radio signals move at essentially the speed of light. A tiny timing error turns into a big distance error, but the satellites are up high, moving fast, living in weaker gravity than the ground, which means their clocks do not match ground clocks by default. At their altitude, the weaker gravity makes the satellite clocks run faster by about 45 microseconds per day. Their orbital motion makes them run slower by about 7 microseconds per day. The net result is that satellite clocks run faster than Earth clocks by about 38 microseconds per day. 38 microseconds sounds like nothing, but light travels a long distance in that time. If you ignored it, the system would drift quickly. Your location estimate would wander by many kilometers as the day went on. It would turn a navigation system into a comedy of errors, so the system includes relativistic corrections on purpose. The satellite clocks are designed and adjusted so that when they are in orbit, their ticking lines up with the time standard the system needs. The algorithms in receivers account for the remaining effects. In other words, modern navigation works because engineers treat Einstein as part of the instruction manual. This is why special relativity is not a fragile theory held together by thought experiments. It is a framework that keeps getting audited by reality, and it keeps passing. Clocks on airplanes, particles in the sky, moons in rings, phones in your hand. And after a century of this, the weirdness stops feeling optional. It becomes normal in the way gravity is normal, not because it is intuitive, but because it keeps showing up. Now, this raises an even sharper question. If relativity is this solid, could we ever find a real exception? Could nature ever allow faster than light motion, even briefly, even under exotic conditions? In the next part, we step into the moment the physics world held its breath, when an experiment seemed to show particles arriving earlier than light should allow, and for a while, the universe looked like it might be about to break its own rules. Every once in a while, science gets a moment that feels like a cliff edge. You're standing on years of careful experiments, a century of theory that keeps working, a mountain of technology that depends on it, and then a result appears that seems to say, actually, no, the universe is not built the way you thought. In late 2011, a team working with neutrinos reported exactly that kind of result. Neutrinos are ghostly particles. They fly through you by the trillions and almost never interact with anything. They barely touch matter, which makes them hard to study, but also makes them perfect messengers for weird tests. They can travel straight through Earth like it is barely there. The team sent a beam of neutrinos from a particle physics laboratory in Switzerland, the European Organization for Nuclear Research, also called CERN, to an underground detector in Italy at the Gran Sasso Laboratory. The baseline was about 454 miles. That distance is big enough that light takes a measurable time to cross it, and if you can time the neutrinos precisely, you can compare their arrival to what light would do. Their claim was that the neutrinos arrived about 60.7 nanoseconds earlier than light would, if light had traveled the same distance in vacuum. That is a tiny number. It is the kind of number you can barely picture, but it is not the size that mattered. It was the direction. Earlier than light. If that were true, it would not be a little update. It would be a demolition charge under the whole structure. Because as we have been building up, faster-than-light signaling is not just an engineering shortcut. It drags you into causality trouble. It creates frames where cause and effect can flip. It opens the door to messages that arrive before they are sent. So the physics community reacted the way it should react, not with applause, with scrutiny sharp enough to cut steel. Other experiments started checking. Other teams looked for the same effect. The analysis was torn apart. The timing systems were questioned. The distance calibration was questioned. The clock synchronization was questioned. People ask the uncomfortable questions that have to be asked when the stakes are that high. And the culture around it got weirdly human, because it always does. One British physicist, Jim Al-Khalili, joked on television that if the result held up, he would do something embarrassing involving his boxer shorts. The joke landed because everyone felt the same thing. This cannot be right. But we cannot dismiss it without checking. That is the part that matters. Science does not respond to extraordinary claims with faith or with anger. It responds with tests. Then the story turned in a way that should make you trust the process more, not less. In early 2012, investigators found a problem in the timing chain. A loose connection in a cable between a global positioning system receiver and the experiment's master clock had introduced a timing error. The size of that error was on the order of 73 nanoseconds, which is already larger than the claimed early arrival. There was also a second issue tied to an oscillator used for timing. That second error pushed in the opposite direction, adding confusion to the picture. But the key point was simple. The experiment had not discovered a new law of nature. It had discovered a new way for extremely advanced hardware to betray you. Once the issues were corrected, the faster-than-light effect vanished. Other experiments did not confirm it. The neutrinos behaved. The speed limit held. Now, it is tempting to tell this story like a near miss, like a scary moment that turned out to be nothing. But that would miss the deeper lesson. This episode is a demonstration of strength. A serious claim was made. It was not brushed aside because it threatened a famous theory. It was not accepted because it sounded exciting. It was hammered with checks until the weak point was found, and it was found within about 6 months. That is how knowledge gets tougher. And there is another quiet lesson hiding under the drama. Measuring something like this is unbelievably hard. You are comparing clocks separated by hundreds of miles. You're synchronizing time at the level of billionths of a second. You're relying on electronics, cables, calibration, and assumptions that all have to behave. One small error can impersonate a revolution. So when relativity keeps passing test after test, it is not because nobody has tried to break it. People keep trying. Reality keeps refusing. Which brings us to the next question. The one that feels less like philosophy and more like destiny. If the speed of light is this stubborn, what does it do to our ambitions, to our technology, to our ability to explore, to how we communicate across space? In the next part, we take the speed limit out of the lab and into the real world. We look at the tools that already depend on it, the machines that push right up against it, and the brutal cost of trying to cross the universe under a rule that will not bend. The speed of light sounds like a limit that only matters for exotic things far away. Black holes, quasars, distant galaxies. But once you connect it to mass and energy, it slides into your hospital, your power plants, and the deepest machines we have ever built. The same rule that blocks you from calling a planet in real time is also the rule that lets us turn matter into energy and back again. Einstein's mass-energy relation is often thrown around as a slogan, but behind the slogan is a simple idea. Mass and energy are not separate currencies. They are two ways of writing the same entry in the universe's ledger. A small amount of mass corresponds to a large amount of energy, because the conversion factor is the speed of a light squared. Multiply that enormous number by even a tiny mass, and you get a frightening amount of energy. You see the shadow of that truth in nuclear power and in weapons that we hope never to use. But you also see a gentler side in medicine. In a hospital, when someone lies down for a positron emission tomography scan, they are deliberately letting a little bit of mass turn into energy in a very controlled way. A radioactive tracer emits particles that annihilate with electrons in the body, converting their mass into bursts of gamma light. Detectors catch those flashes and build a picture of what is happening inside living tissue. That scanner only works because the bookkeeping between mass and energy is precise. The energies of the gamma rays are fixed by the masses that vanish. The patterns reveal where the tracer is gathering, how organs are behaving, how a tumor might be feeding. It is relativity, not as an abstract theory, but as a medical tool humming quietly in the background while someone lies still and tries not to think about what the results might say. On the other end of the scale, the Large Hadron Collider pushes the same rule to the edge of what humanity can engineer. In that machine, protons are whipped around a ring many kilometers long. Superconducting magnets bend their paths, keeping them confined as their energy climbs higher and higher. The protons move so close to the speed of light that, from our perspective, you have to multiply their mass by many times to account for their resistance to further acceleration. That extra effective mass is energy stored in motion. When two of those protons collide head-on, the energy in their motion does not just vanish. It has to go somewhere, and the universe spends it by briefly creating new particles that did not exist before the collision. Massive particles that normally would be far beyond reach appear for an instant, then decay into showers of lighter fragments that the detectors can see. Again, the speed of light is encoded in the process. The relationship between the energy you pour in and the masses you can create includes that same conversion factor. When the Higgs boson was discovered, it was not because someone found a little marble hiding in the ring. It was because enough energy was pushed into a tiny region of space-time that reality could briefly afford an excitation of that field. Mass and energy traded places under the same rule that caps how fast any signal can travel. So the speed of light is not just saying no, it is deciding how expensive yes will be. You feel that cost even more brutally when you think about travel and communication in space. Light speed is generous on human scales. Talk to someone across a room and the delay is too small to notice. Talk to someone across a city and the delay is still harmless. Even across Earth, a signal can circle the globe in a fraction of a second. Video calls feel immediate, and we build a habit of expecting that kind of responsiveness. Then you step away from the planet, and the illusion breaks. The moon is close by cosmic standards, only about 1.25 light seconds away on average. That means a radio signal takes a little more than a second to get there, and a little more than a second to come back. If you were standing in a control room talking to an astronaut on the lunar surface, the conversation would feel like speaking with a polite echo. You say something, there is a gap, they respond. There is another gap. You would adapt, but you would feel the distance as silence between sentences. Stretch the distance to Mars and the silence turns into waiting. Depending on the positions of the planets, a one-way signal can take anywhere from a few minutes to more than 20 minutes. A round trip can eat up close to an hour. You cannot joystick a rover in real time with that kind of lag. By the time you see what it did in response to your last command, you have long since sent many more. So missions to Mars are designed around autonomy. Rovers carry software that lets them navigate, avoid hazards, and choose targets with only general guidance from Earth. The humans send high-level plans. The machines do the moment-to-moment work. That division is not a choice born of laziness. It is forced on us by the speed limit. The universe will not let your intention outrun the radio waves that carry it. Now push out further. Spacecraft at Jupiter, Saturn, or beyond send signals that take tens of minutes or hours to arrive. The Voyager probes, wandering now far past the outer planets, talk to us on a delay measured in many hours. commands ride on beams of a light that cross the darkness slowly compared to the size of the journey. When the spacecraft answers, the reply is already old when it arrives. Those machines are not just far away in space, they are far away in time. You never know them as they are right now. You only know them as they were when their last signal left. This is the real emotional cost of the speed of light. It turns space exploration into a sequence of postcards. You launch a probe, you wait. It sends back a picture of a storm on Jupiter, a glimpse of Saturn's rings, the soft glow of a distant moon. Every time you see one of those images, you're looking into the past. The deeper you go, the more the past stretches. Imagine carrying that into human voyages. If people ever orbit Mars for real, they will be on the far side of a light-time wall. Families back on Earth will not be able to call and chat freely. Every hello will sink into a gap of minutes. Every laugh will arrive long after the joke was told. Every urgent question will already be stale by the time the answer comes back. And yet, the same rule that makes conversation slow also guarantees something profound. No matter how advanced a civilization becomes, no matter how strong its transmitters are, no matter how clever its encoding gets, it cannot turn the galaxy into a real-time network. Every world will live behind its own delay. At interstellar distances, the gaps are measured in years. Even if you found a planet with an intelligent species around a nearby star and began exchanging messages, you would never have a conversation in the way we mean that word. You would be sending letters. You would be talking to the past and planning for a future you will never see. The speed of a light gives us energy, structure, and a way to turn mass into medicine and discovery. But it also writes loneliness into the architecture of the cosmos. It says that the universe is connected, but only slowly. That knowledge, emotion, and warning can spread, but only at a fixed pace. So it is no surprise that our stories are full of dreams about beating that limit. Hyperspace, subspace, warp drives, wormholes, teleportation. We keep inventing fictional tools to erase the waiting, to punch through the light cone fence. In the final part, we walk through those dreams and hold them up against what physics currently understands. We look at the loopholes people imagine, the exotic ideas that might bend space-time, and the one remaining mystery that sits behind all of this. Not whether the speed limit is real, but why it has the value it does at all. So far, we have treated the speed of light as a kind of local rule. Signals can only move so fast. Spaceships can only accelerate so far. Conversations pick up delay as distance grows. That is already enough to make the universe feel large and slow. But there is another layer to the story that is almost unfair. Space itself is stretching. While light is doing its best to cross the void is quietly getting bigger under its feet. Imagine painting tiny dots on the surface of a balloon. The dots are galaxies. As you blow air into the balloon, the distance between the dots grows. None of the dots are crawling across the rubber. They are staying put on the surface, yet they move away from each other because the surface itself is expanding. That is the basic image behind cosmic expansion. On the largest scales, space is not static. It grows. Galaxies are carried along with that growth. When we look out, we see distant galaxies rising in redshift, their light stretched to longer wavelengths by expansion that happened during its journey. Now add light speed to that picture. When you look at a distant galaxy, you are seeing light that left it long ago. Suppose the light has been flying toward you for billions of years. While that light has been traveling, space has been expanding. So the galaxy that emitted the light is not only far away because the light had to cross a distance. It is also farther away now than it was when the light left, because the universe has grown in the meantime. This is why the observable universe is larger than you might expect. The universe is about 13.8 billion years old, but the radius of the region we can see is much larger than 13.8 billion light years. The light has been moving toward us for that long, but the space it travels through has been stretching. By the time the photons arrive, the sources that emitted them are now tens of billions of light years away. Already you can feel a new kind of horizon forming. There is a distance beyond which we cannot see, not because our telescopes are weak, but because light has not had enough time since the beginning of the universe to reach us. That boundary is the edge of the observable universe, but there is a sharper boundary hiding behind it. As space expands, distant galaxies recede from us. The farther away they are, the faster that recession. Not because they are firing rockets, but because more expanding space lies between us and them. At some distance, the recession speed reaches the speed of light. Beyond that, the distance between us and those galaxies is growing faster than light speed. This is where people often get nervous, because it sounds like the universe is breaking its own rule. How can anything move faster than light? The key is to remember the difference between motion through space and motion of space. Relativity forbids objects from moving through space faster than light in a local sense. It does not forbid the distance between two far apart objects from growing faster than light if the growth is due to expansion of space itself. No signal can ride the expanding fabric and outrun a light beam traveling locally in its own patch. But from our perspective, the gap between us and some distant galaxy can still grow faster than a light beam could ever close it. Once that happens, a new kind of horizon appears. For galaxies beyond this region, no signal we send today will ever reach them. Even if the universe lasts forever, the expansion will always win. The light will always fall behind. Their future is sealed off from ours by geometry. That horizon defines the largest possible sphere of two-way communication. Inside it, there is at least in principle a chance to send a message and receive a reply. Outside it, there is not. Those parts of the universe are not just unvisited, they're uncontactable, and the line is not stable. As time passes, more galaxies drift beyond this communication horizon. The observable universe grows as light from more distant regions finally arrives, but the reach of possible conversation shrinks. Far future astronomers will live in a sky that has lost most of its galaxies to the dark, not because the galaxies vanished, but because their light can no longer reach. Now bring this back down to the scale of our own galaxy, and the question that quietly haunts a lot of cosmic thinking: where is everybody? The Milky Way is big, but not incomprehensible. It is on the order of 100,000 light-years across. If an advanced civilization wanted to send a signal from one side to the other, light could do it in 100,000 years. That is a long time for a human, but short compared to the age of the galaxy. You might think that would be enough to fill the night with messages, but even inside one galaxy, the light speed limit turns communication into a story that unfolds in slow motion. Imagine two civilizations separated by 10,000 light years. They build radio telescopes that are perfect. They discover each other. They begin to exchange messages. Each line in the conversation takes 10,000 years to arrive. The reply takes another 10,000 years to come back. By the time the third or fourth back and forth is complete, entire cultures could have risen and fallen on each side. The people who receive the messages will not be the people who sent them. Every new line of dialogue would be an artifact from a civilization that may already be gone. That does not make communication impossible. It makes it heavy. It turns every message into a time capsule, every reply into a work of archaeology. The relationship between worlds becomes less like conversation and more like exchanging carved stones across ages. And that is assuming nothing worse than distance. Real galaxies are messy. Stars move, orbits shift, planets freeze or fry. Civilizations face their own internal hazards. The light speed limit does not just slow their messages, it delays their warnings, their offers, their cries for help. So the silence we hear when we listen for signals from the stars might not mean we're alone. It might mean everyone is talking very slowly across enormous gaps, and we're arriving in the middle of a conversation that spans millions of years. Or it might mean many voices never lived long enough to speak across those gaps at all. The speed of light does not prefer despair. It does not care. It simply enforces a world where connection is possible, but never instantaneous. Where knowledge can spread, but never outrun time. Where even if the universe is full of life, each island of intelligence must live with long stretches of not knowing who else is out there. There is something quietly honest about that. The same rule that lets us read the afterglow of the Big Bang, that lets us reconstruct the history of galaxies billions of years old, also guarantees that we'll never see the entire universe as it is in one single moment. We always see a patchwork of different eras, stitched together by light that has traveled different distances. We live inside a horizon. We always will. Beyond that horizon, reality exists whether we witness it or not. So it is no surprise that our imaginations keep reaching for an escape hatch. A way to fold space, tunnel through it, or skip across it so that the light cones bend in our favor. In the final part, we walk through those dreams. We look at entangled particles, hypothetical faster-than-light carriers, warped space-time, and exotic tunnels. We see which ideas are already ruled out, which ones are still clinging to the edge of possibility, and what they all say about the deepest question hiding in that single number at the heart of this story. The moment you tell people nothing can go faster than light, the next question is always the same. Are you sure? It is a very human instinct. We hear the word limit, and we immediately start looking for a side door. Maybe there is a trick. Maybe there is a special case. Maybe there is a way to obey the letter of the law while gutting its spirit. Physics has chased those maybes hard. What survives that chase is not a list of cheap hacks, but a clearer sense of how tightly the universe protects causality and how much imagination it still invites. Start with something that looks suspicious from the outside. Quantum entanglement. If you take two particles and prepare them in a shared quantum state, they can become entangled. Measure one here, and you instantly know what you will get if you measure the other over there. People love to describe this as spooky action at a distance. It sounds like a perfect faster-than-light telephone. Flip a setting on one side, read a response on the other, except you cannot. The catch is that the individual outcomes are random. You cannot choose what result you will get on your side. You and your distant friend can only see the pattern when you later compare notes with good old slower-than-light communication. The universe does not let you encode a controllable message in the entangled correlations. That rule is sometimes called the no communication theorem, and it quietly keeps quantum weirdness from wrecking space-time. Entanglement lets the universe coordinate outcomes in a way that is deeper than classical physics. It does not let anyone send usable information outside the light cones. Nature gives you mystery, not a shortcut. Next on the wish list are tachyons, hypothetical particles that are born faster than light and never slow down below it. On paper, you can write down such things. In some mathematical toys, they appear naturally. They look like a perfect way to move signals around without waiting. Then you chase the consequences. If a particle always moves faster than light, there will be reference frames in which it travels backward in time. That by itself is not illegal, but once you can send a tachyon from point A to point B, and someone else can send one from B back to A, you have the same nasty loop we built earlier, with a hypothetical faster-than-light radio. In some frames, the reply lands before the original message was sent. The contradictions show up again. On top of that, we have never seen any sign of such particles in the wild. High-energy experiments around the world are constantly producing and tracking particles at extreme energies. They see things that behave exactly as you would expect from relativity. Nothing that looks like a stable population of faster-than-light travelers. So tachyons remain what they started as. A useful warning about how quickly causality unravels if you try to push signals beyond the limit. rather than a serious candidate for getting around it. Science fiction often skips past particles and jumps straight to engines that reshape spacetime itself. Warp drives and wormholes. The basic idea of a warp drive is seductive. General relativity, Einstein's theory of gravity, does not forbid spacetime from stretching. We already live in a universe where entire galaxies move apart faster than light due to expansion, without any local violation of relativity. So what if you could engineer a small version of that around a ship? Compress space in front, expand space behind, and let the ship surf the distortion. Inside the bubble, you never move faster than light relative to your local space-time. Yet from the outside, you seem to cross enormous distances in less time than light would need in undistorted space. Written that way, it feels like a loophole so clever it deserves a prize. Then the bill arrives. Calculations suggest that to create such a bubble, you would need negative energy densities, regions where the energy of the vacuum is less than what we normally call empty. Quantum physics does allow tiny, fleeting negative energy effects in special situations, but everything we know so far suggests there are strict limits on how much you can have and how long you can keep it. The amount you would need for a useful warp bubble is absurd, and may not be possible at all without tearing up other parts of physics. Wormholes are another favourite. Take two distant points in space-time and connect them with a short tunnel. Fall in here, pop out there. Again, on paper, you can write down spacetimes that contain such tunnels. In some versions, they behave like natural bridges. In others, they act like potential time machines, letting you take a path that effectively sends you into your own past. Both stories run face first into the same guardian. To keep a wormhole stable and open wide enough to travel through, you again seem to need exotic matter with negative energy density. Quantum field theory hints that the universe fights such configurations with fierce restrictions. You can have little glimpses of exotic behavior, but not enough to build a human-sized door through space and time. And even if you could, the time travel aspect would resurrect causality problems in full. Once closed loops of time are possible, you're back in the land of messages that erase themselves and events that cannot decide whether they happen. So the most serious work on warp drives and wormholes today tends to be less about engineering and more about using them as thought experiments. They test how strong our assumptions really are. They map out the boundaries of what relativity and quantum theory can tolerate. So far, the boundary seems to stand firm. Yet the universe does allow a few odd edge cases that sound faster than light if you phrase them carelessly. In a transparent material like water or glass, light travels slower than its vacuum speed. A charged particle passing through that material can sometimes move faster than light does in that medium, while still remaining slower than the vacuum speed limit. When that happens, the particle emits a glow called Cherenkov radiation, a kind of light boom similar in spirit to a sonic boom. The famous blue haze in nuclear reactors comes from this effect. It looks like a particle outrunning light, but nothing fundamental has been broken. The particle is still slower than light in vacuum. No information has leapt outside its allowed cone. The rule that protects causality remains untouched. On cosmic scales, some jets streaming from around black holes or active galaxies appear to sweep across the sky faster than light. That effect too is a trick of geometry. The jet moves very close to the speed of light at a narrow angle toward us. Light from later positions of the jet has a shorter distance to travel than light from earlier positions. When you project the motion on the sky, it can look like the feature is crossing space faster than light, even though locally it never does. Once again, the universe lets appearances play, but keeps the underlying structure safe. So after all these paths and near misses, we end up back at the same quiet puzzle that has been hiding behind the story from the beginning. Not whether there is a speed limit. We are past that. The experiments have hammered it in too deeply. The real question is why the limit has the particular value it does, and what that value truly means. In our human units, The speed of light is a huge number, in natural units that physicists sometimes use. Where space and time are scaled differently, that number becomes 1. The constant turns into a simple conversion factor between units, like a rule that says so many meters of distance correspond to so many seconds of time. In that view, the speed of light is less a bolt of lightning and more a statement about how space-time is stitched. Yet the constant also appears inside deeper combinations. It helps set the strength of electromagnetism through dimensionless quantities. It shapes how particles interact, how atoms form, how stars burn. Change its value enough and you might not get stable atoms or long-lived stars or chemistry that can support something like us. This leads some thinkers to an uncomfortable thought. Maybe the reason we observe this particular speed of light is that universes with very different values do not make observers very often. In a vast landscape of possible physics, most combinations of constants would produce sterile expanses or brief flashes of structure. We happen to live in one of the rare sets that allow galaxies, planets, long chains of cause and effect, and eventually creatures that ask questions about it. That line of reasoning is often called anthropic. It does not really explain why the number is what it is. It just says universes where it is very different are not the ones in which anyone is around to complain. It feels more like a shrug than an answer. So the mystery remains. We can write down how the speed of light enters our equations. We can see how it corrals causality and sculpts space-time. We can measure it to absurd precision and even build our rulers and clocks around it. But why the universe chose this rule and not another is still open. Maybe one day a deeper theory will show that the value of the speed of light is not a choice at all, but an emergent fact from an even more fundamental layer of reality. Maybe it will always be a boundary condition, something we take as given in order to ask other questions. Until then, we live as slow creatures under a far ceiling, watching ancient light fall out of the dark. Every star we see is a delayed message that obeyed the same rule. Every signal we send to a spacecraft or a future telescope rides the same limit. The speed of light locks us into a universe where nothing happens everywhere at once, where stories unfold inside cones of influence, and where knowing anything takes time. That can feel like a cage. It can also feel like a gift. Because without that structure, without that single number holding cause and effect together, there would be no stable past to remember, no reliable future to plan for, and no long cosmic journey for minds like ours to slowly understand.